Just by your
Okay. Hi, thanks for inviting me. So what I want to tell you about now, I guess two words that have the same flavor. And this flavor is that sometimes just the simplest solution, which is just based on random sampling, works in the adaptive setting and kind of actually gives better results than prior construction that people thought. Okay, so the first result is about some problem that's called distributed counting. Okay, it's joint work with it and our joint student, Moshe Sherer. So what is distributed counting? In this problem, we have a server and we have k sites. Throughout the execution, at every timestamp, a different site gets an event. And the goal of the server is to continuously track or approximate the total number of events that have occurred till now. Okay, so here is an illustration. This site maybe gets the first event, the server wants to say 1. Then this site gets an event, the server wants to say 2. Another site gets an event, the server wants to say 3, and so on. And of course, the server doesn't have to give an exact count, but it wants to give an approximate count. Okay, so capital N is the total number of events, K is the number of sites, epsilon is our approximation parameter. And the goal in this problem is to do it while minimizing the communication complexity in your protocol. You want to minimize the communication between the sites and the server. So what do we know about this problem? First, if you want deterministic protocols, then we basically know the answer exactly. Okay, so known results from 06 even say that if you want a deterministic protocol, then it suffices as necessary to have overall communication complexity k over epsilon times log. What about randomized protocols? So Hang et al. Showed in 2012 that if you use the randomized protocol, then you can save a root k factor in your communication complexity. Okay, the communication drops from k to root k over epsilon times log. But, I mean, the protocol only works in the oblivious setting. Of course, it's from 2012, right? Nobody really thought about that setting back then. And so recent work showed from 2023 showed that basically you could take that oblivious randomized protocol or some version of it and make it robust.
I think that there was a question.
Yeah. I was sorry. There's a model that like the sites like observe events like spontaneously,
Yes,
and then
yes.
like and spontaneously decide to send events.
Yeah, exactly. The model is that the sites observe events spontaneously, then they could keep quiet, or they could send something to the server. It's event-driven. Everything is
going to get back to them instantaneously, or like sort of decide whether or not.
I mean, nothing happens. All of the picture is event-driven, so nothing happens without an event. Event to the site could trigger something, and then it could trigger the server to doing something else. Okay, but when there is no event, then everything is false. Okay, so where was I? You could take that result show that you could take this oblivious protocol or some version of it and make it robust, basically via this robustification via differential privacy generic technique. They take this protocol or a version of that protocol and hide its internal randomness using techniques from differential privacy. I don't know if you're familiar with it, but some kind of a binary tree for continual counting and sparse vector technique. Anyways, it's not too bad, but it adds algorithmic complexity and it costs you another polylog k factor in the communication complexity.
So just another question about the model. So you assume that the adversary controls all the sites.
The adversary controls the sequence of events going to each of the sites.
Yes. But does the adversary see what the sites send to the server?
Right. So in that model, right, no, the sequence is fixed in advance. In this model, no. So that's why I wrote this as one of the shortcomings of this solution. It's only robust in what's called the black box adversarial model, in which the adversary only gets to see the approx count by the server, and based on that chooses the next site which will get an event. Okay. So these are the three shortcomings of this solution. I guess somewhat complex algorithmic solution, extra polylog in the communication complexity, and only black box. Well, basically, what we show first, it's easy to show, but we need to do it. It needs to be done. We show that this protocol is indeed not robust. This original randomized protocol is indeed not robust. And if the adversary sends the updates to the sites based on the outcome of the server, then this protocol breaks. The adversary can fool this protocol. And the same proof also shows that this protocol is not white box robust, only black box robust in the sense that if the adversary sees the communication, then it can also break this protocol. Okay? And then what we show probably maybe the simplest protocol that you can think of that just uses random sampling. I'll show it to you in a minute. It's both robust. It doesn't use any external robustification techniques. It just uses random sampling. It has the optimal communication complexity for the randomized algorithms, and it's white box. Okay, so now the adversary is allowed to see internal communication and inner state of everyone. More questions?
Is it only insertion only string or insertion?
Yeah, so there is no notion of insertion or deletion. It's just a site. I guess you could say that it's insertion only. As time goes by, the number of events just increases. Yes. Okay, so here is the protocol. The protocol operates in rounds, and first let me tell you what happens in the beginning of the round. In the beginning of the round, the server notifies all of the sites that the current round has ended and that the new round begins, and collects from the sites from every site the server collects the exact local counter of these sites. So in the beginning of the site, the server knows the exact count till now. Right? So let's denote by n0 the exact counter of all of the events that happened till now. From this n0, the server defines some parameter p, which I'll call the transmission probability. It's roughly root k over epsilon times n0, and sends this transmission probability, this parameter p, broadcasts it to all of the sites. Okay, that's in the initialization over the round. Then during the round, whenever a site gets an event, it flips a coin, and with probability p, it sends the message 1 to the server. Otherwise, it stays quiet. Okay. And so throughout the round, let's denote by capital B the number of 1 messages that the server has got till now, from the beginning of the round. And then the server estimates the total count of events so far in the way that you would expect it to do, right? It's n0, the number of events in the beginning of the round, which the server knows exactly, plus capital B over P, which is the expected number of events that has occurred if the counter of 1 messages is B. Make sense? And so that's what's going on within the round, and the round ends when B is K. When the server gets message number K, then round ends, server notifies everybody that the round is ended, and so on. Okay, so if just to say it, the number of events within the round is expected to be K over P, which by the choice of P is roughly epsilon times root K times N0. Yeah.
So, I mean, like, it's like the version, like, in advance, no, like, variable, or like, how do
You say again,
Like,
I understood.
like, how do you, like, get?
Yeah, so the P is computed, it's only a function of N0, right? And so in the beginning of the round, the server collects exact counts, it knows N0, P is the term, and then it broadcasts P to all of the sites. Okay. Yeah? More questions? Is the protocol clear?
So in this round, the value, the n0 is actually increased by like way more than 1 plus epsilon, right?
Mm-hmm. Yeah, increased by that. From n0 to epsilon times root k times n0 plus n0. Okay. And kind of the key new property in this protocol compared to the previous 2 randomized protocols that I surveyed is that this protocol is symmetric with respect to the sites. At any given moment, all of the sites are equal. It doesn't matter which site gets an event. The protocol behaves exactly the same. In particular, it's easy to see that the outcome distribution of the server is independent with respect to which site gets the next event. And that means that the adversary might as well just send all of the events to site 1, which is an oblivious string of rules. So you're taking away its power, right? Oh. So what I'm saying is it suffices to analyze the accuracy of this protocol in the oblivious set. So let's do it. How do we analyze roughly the accuracy of this protocol in the oblivious setting? So like we said, during the round, the server sees exactly K1 messages. And if you think about it, how is the exact number of events during the round distributed? It's distributed exactly as the sum of K geometric random variables with parameter P. So at the end of the round, the count is B equals K, and the actual count of events is distributed as the sum of K geometric random variables. And after N messages, we estimate the count as N0 plus L over P, and the actual count is distributed as N0 plus the sum of L geometric random. So all you need to do is use tail bounds for partial sums of geometric random variables and see that the difference between that and that is small. Yeah.
So this is just basically a distributed kind of Morris counter, right?
I guess so, yeah. More questions? Okay, so what about communication? Like you said, Samson, from round to round, the N0 increases by that factor. So it says that, you know, the number of rounds is logarithmic with that base. And within every round, the communication is exactly K, because you have K1 messages, so it gives you the correct communication complexity.
You also need a plus K number.
Yeah, it's hidden. Right. All of these random protocols have this hidden here.
Oh. So continuing the Morris counter equation, why do you need the logarithmic and non-product?
Yeah, I'll have to think about it, but you can't go below that. Particularly, these guys in the same paper show that that's tight. Okay. Okay, so basically that's all I wanted to tell you about this book. Yeah.
Sorry, so is the construct out of not
And so all of the works in this vein, the communication complexity is counted by number of messages. I should have said that, not bits, but you could transform it into bits, and then you could pay another some log anything. Okay, you could transform it into bits. The way I presented it and the way all of the previous works present it is counting number of messages.
So the lower bound also applies.
Yeah, number of messages. Yes, number of messages.
So here, so you need to assume that K is smaller than highlight and overlap well, something.
Yeah, you need to assume that. That's your assumption that you have for.
Oh, I see.
Okay. Okay. What do you say? Go on to the next paper? That's all I wanted to tell you about this. So the next work is joined with Chaim Kaplan and Adi Fine. And before reading the title of this paper, let me tell you the motivation behind this line of work. Okay, so what is a graph spanner? A spanner is a subgraph which is supposed to be a subgraph of G, which is supposed to be sparse, but nevertheless preserves distances, approximately. Okay, so specifically you have some stretch parameter T, and H, which is a subgraph of G, is a T spanner if every distance is inflated by no more than a T multiplicative round. Right, so here is an example of a tree spanner. I didn't actually check that it's a tree spanner, but I took lots of edges where it has to be a tree spanner. Okay. So in the offline setting, we can construct such spanners very efficiently. Okay, you take a graph G and a parameter K, and you construct a spanner in linear time, O of n time, and and this spanner has the optimal number of edges that you can get, right? So we actually know that if you want to construct a spanner with that stretch, then the optimal number of edges that you need is that under some guilt assumption, conjecture, which I'm not going to. Let's just say this. Okay. So in the offline setting, it's great. Linear time, optimal in terms of the size of the spanner, and we're ahead. What happens in the dynamic setting? In the dynamic setting, right, as you would expect, the story is that the graph G is not fixed in advance. Instead, the graph G undergoes edge insertions and deletions, and your goal is at every time step, you want to maintain or output a T-spanner for the current state of the graph G. Make sense? What happens if the sequence of edge insertions and deletions is fixed in advance? So we're in the oblivious setting. Basically, there are some lower order questions here still left, but basically problem solved. For any K, you could maintain a spanner with that stretch with roughly optimal size in terms of the number of edges in the spanner that you're maintaining. And the main quantity that you care about is the runtime per edge insertion or deletion. And in the oblivious setting, the runtime you need per edge insertion or deletion is polylog n. So we're happy. Again, there are lower order questions here, but at the high level, problem solved in the oblivious setting. Okay? What happens in the adaptive picture? So we have huge gaps between what can we do in the oblivious setting and what can we do in the adaptive setting. So here in the adaptive setting, the adversary at every step of the way, it sees the spanner that you're maintaining, and then maliciously decides, okay, I'm going to add that edge, or okay, I'm going to remove that edge, and so on. So for a long time, the only thing that was known in the adaptive setting were these deterministic constructions of a 3 or a 5 spanner, which has the correct number of edges, so the size of the spanner is correct. Problem is, it's very slow. Per update, in this deterministic construction, you pay O of n time. Not happy. Okay, so recently in 2022, we have 2 papers showing or trying to argue with this. So what are the results that we know? First, if you're willing to go all the way up to polylog n stretch, so your spanner is not very good in preserving distances. It preserves these distances up to this polylog n factor, but it's not, I guess, yeah, if you're okay with that stretch, then you could dynamically maintain a spanner with the roughly the correct number of edges and spend only polylog n time per edge insertion or edge. In other words, if you're willing to have that large of a stretch, problem solved. If not, then the only construction that was known, that still is known, is a 3 spanner with the correct number of edges, runtime per edge insertion or deletion routed. Not trivial, not very good, right?
Can a GPU be wicked one?
Can what?
GPU wicked one?
I think that in most of these results, yes, but it has some kind of a trade-off. Okay, but the way I wrote it is for unweighted graphs. Most of these results have analogs for weighted graphs, but I didn't. I don't remember the trade-off, and we tried it here. Okay. Okay, so you see there are huge gaps between the adaptive and the oblivious setting, and because of that, then these 2 papers, they started looking at a different measure for the efficiency of dynamic algorithms in this context, called the recourse. So what is the recourse of an algorithm? It's the number of changes you need to do to your data structure for every update to your input. So if the recourse bound is 3, that means that for every edge insertion or deletion, you're allowed to change at most 3 edges in the spanner that you're maintaining. Okay, so lower recourse is good because, at least intuitively, if the recourse is high, then intuitively at least you don't have a very good chance of designing an algorithm with low runtime, right? So that's what they showed. What I'll tell you about now are just a little bit about how do we argue with this thing and give a simpler algorithm with lower recourse. The recourse will be log n instead of log cubed n. Okay, that's what I'll show you.
What recourse?
Recourse is the number of changes you need to do to the data structure you're maintaining per update. So if the recourse is 3, for every edge insertion or deletion, you are allowed to change 3 edges in the spanner you're maintaining.
Are you need more update time?
Oh, so the update time at any case, I wish it was smaller, but the update time will stay rooted. Okay? Okay. And actually, the problem so the motivation comes from spanner, but the actual problem that we solved in this paper is a different load balancing problem that the previous paper reduced the 3-spanner problem to. Okay, so instead of designing a spanner, we just need to solve this load balancing game. So what happens in this load balancing game? You have a bipartite hypergraph. One side is n jobs, one side is n machines. Every hyper edge here, it touches one job and multiple machines. Okay? And your goal is to, at every step of the execution, maintain an assignment. What is an assignment? An assignment is just, you need to select exactly one hyper edge for every job. The interpretation is that if you chose this hyper edge to this job, then this job is kind of running on these 2 machines right now. Make sense? So you need to choose some initial assignment. Then the adversary sees the assignment that you chose and decides on a machine to destroy. The adversary kills this machine goes away, and then all of the hyper edges that touch it also go away. So this edge goes away, but also the other edges which are not selected in the current assignment, they are also going away. As a result, some of the jobs now become uncovered, right? I need to recover them. So for every uncovered job, I need to choose a new hyper edge to cover it, and my risk to reassign. That's my price. So in this example, these 2 jobs became uncovered. I chose different hyper edges for them. They are uncovered. Now the adversary sees the current picture, decides on the next machine to kill, kills it. Hyper edges that touch it go away. You need to recover this thing, and so on. Questions? Okay, so what do you want? You want to design, so this goes on, let's say, for 3 rounds. You want to design an algorithm that's fast. You don't want to spend too much time on every operation of the adversary, and you want to have low recourse. So what the previous paper did, here's their bound. Their algorithm guarantees recourse of that magnitude. So let's read it together. N is the number of jobs, M is the number of machines, T is the number of steps. So if you think about it, it's quite good, right? Because if there are T rounds, then of course the adversary could accumulate recourse linear in T. In every iteration, it's going to delete some hyper edge. You're going to need to reassign at least 1 job. So the fact that this is linear in T, that's unavoidable. So in their bound, it's multiplied by log squared M, no biggie. And that thing, it's also not too worrying because it's aggregated across all of the T steps together. Okay, it's not multiplied by T. And the way that they designed their algorithm is based on a technique that appeared also in different papers called proactive sampling or proactive resampling. So what is the algorithm? What is the algorithm? What does it do? First of all, whenever a job becomes uncovered, you sample a random hyperedge for it. Okay, makes sense. You have to cover this job somehow, you do it. But in addition, and that's the proactive sampling thing in their paper, whenever a job becomes uncovered and you sample a fresh, an existing hyperedge for it, you also commit to logarithmically many future time steps at which you will resample an edge for that job no matter what, even if it's still covered at that moment. Okay? Somehow they leverage these future resampling times in order to show kind of a sophisticated charging argument that kind of charges the recourse that the adversary does at every moment to future resampling that you're committing to, and using that, somehow they were able to show that bound. Make sense? What we show is basically that you don't need this resampling thing. Just whenever a job becomes uncovered, just randomly sample a fresh edge for it, and that's it. That's all of the algorithm. And it works in the adaptive setting, and not only does it work in the adaptive setting, it also shaves off a log squared m factor from here and the log m factor from here. And when you go in the reduction back to the three spanner, this improves the recurse of the resulting three spanner by a log squared n. Okay, so and the technique that we use in order to analyze this simple just random sample and edge whenever necessary algorithm is by kind of relating this load balancing game to a simple adaptive version of balls into bits. Okay, so let me go back to this picture. So that's why the machines here looks like bins in my slides. So let's simplify the problem. Suppose that the hypergraph, that the bipartite graph is not a hypergraph, it's just a bipartite graph. Okay, so all of the edges are just edges. Every ball can go into one machine. And also, to simplify things, let's assume that it's a complete bipartite graph. So every ball can go into every machine. Okay, so in that situation, initially, and also to simplify even more, let's say that n equals m. You have n balls, n bins. Initially, you just throw all of the balls into the bins. The adversary looks at the assignment, deletes a bin. The balls in this bin are redistributed randomly across the remaining bins. The adversary sees the constellation, deletes a bin, and so on. And it somehow turns out that it suffices to analyze this simpler problem, and from that analysis you could extend it to the load balancing game that we showed before. So I think you got it already, but here is a picture. Initially you just throw n balls into n bins. The adversary sees that, chooses a bin to delete. The adversary gains 2 because it deleted. It forces you to redistribute 2 balls. This bin goes away, its balls are redistributed. My cost is 2. The adversary sees this, decides on a bin to delete. The adversary gains now total 5. Yeah.
So at every step, why wouldn't the adversary just pick the heaviest bid?
Yeah, that would be the optimal strategy for the adversary. You could show, you need to prove that, but you can prove that, and it's correct. It would be, I mean, it's not totally clear a priori that that's what you want, but it is true that it's optimal for him. Okay, anyways, the adversary choose this bin, redistribute it, and so on. Chooses that being redistributed, and so on until at the end all of the balls are in the same bin. That's when the game ends. And the question is, how much recourse can the adversary have during this process? And so it's not an open question, it's a simple exercise. It's written in the paper. Once you simplify the game so much, then it's not too hard to show that no matter what the adversary does, in particular, that's the best thing he could do, that's the maximal number of balls reassignment he could have. So I'll just finish here by saying that if you try to formalize this, I mean, it's very intuitive that that's the correct thing. Let's think even that the game continues only n over 2 steps. So you start with n bins, and the game ends when you have n over 2 bins. So right, we all know that initially the maximal load of a bin is less than log n, right? So it's very tempting to say, okay, then initially the adversary deletes a bin of size log n, then somehow in round 2 also the maximal load is log n, and somehow in every round the adversary deletes only bins with log n. So if you continue till n over 2 steps, then it's order of n times log. How would you prove that? I mean, problem is, after a few deletion steps, the assignment of the balls into the bins are not really random. it's somehow adaptive based on the choices of the adversary. So how would you formally prove this? That's kind of, again, it's not an open problem or something. It's an easy exercise. I'm just leaving you ending my talk with this easy exercise. Okay.
So, the algorithm allowed to move around balls even if it doesn't need to?
Sorry.
Is the algorithm allowed to move
Yeah,
around
then you
balls
pay.
even if it doesn't need to?
Yeah,
and pay.
Yeah,
I guess that corresponds to this proactive.
that's corresponds to the one.
Yeah.
So if I understand correctly, does it basically start with random generation and then kind of picks up on a pattern?
It starts with a random assignment, and then what is the second part of the question?
And then does it eventually pick up on a pattern?
On whose part, I'm not sure.
Like pattern of what to delete next, kind of, does it like adopt?
So I guess that as we show, or specifically that part is not in the paper, it's in Adil's thesis. The best thing that the adversary can do is just delete the maximal load of the bin, and look at the bins, look at the maximal load at any bin and delete that. So that's basically the pattern of the adversary.
Yeah.
And you, given that you know that that's the optimal adversary strategy, then somehow you want to prove that it cannot end with rigors bigger than n on n.
So this is unrelated to the application, but it's a very cool Boston, right? It's a very simple but really cool model. Like, what happens if you do these fancy like power of two choices, but now it's arbitrary also for this game? Would you expect the recourse to be n log n, or would you just see totally different behavior?
No, it's not going to be n log n. Even if you do, the expensive thing and you distribute the balls exactly equally likely, you're going to end up with a total of n log n recourse. Yeah, but you're right that there are several variants of this question that I like very much. For example, the way I presented it, once the adversary kills a bin, the balls are redistributed completely. But you could say, okay, continuing with your power of two choice question, I'm not redistributed them completely. Redistributed them. I'm picking 2 or 3 bins, and balls go to these 3 bins, right? Yeah, I think it's a good question. Problem is that Adi finished his thesis and gone away, but I think it's a good question.
Any other questions? Can I ask one about the first one?
Yeah.
Have you considered the other range of epsilon, like, when epsilon is bigger than 1 or 3?
Yeah.
Is there, I was wondering, if you lose some communication here, for example, if you only want to achieve like k-ref, so, is your, some variance of your algorithm will work?
Yeah, so yes, the algorithm would work. Basically, the only thing that's changing is the analysis of the communication complexity, because somehow going from here to here, we use this assumption that epsilon is small. Otherwise, this transition is not true, but everything else remains true. Okay. So the analysis extends to the other regime. You won't get that communication complexity, but you get some of it.
Okay, let's give Uri a round of applause and